Okay, so let's start now. So one of the things in the tutorial sheet was this question 0, which was 2 exercises from the textbook. I'm not sure if you guys have access to the textbook. You can probably find the exercises online. The exercises are worked out in the textbook as well, but I'm going to go through them here. Tim asked me to go through them specifically, so let's do them. So exercise 11.2 basically says derive kt log of the grand partition function equal to PV by using the Boltzmann entropy. Okay, so what we start off with is our probability distribution in the grand canonical ensemble. So we have our states, the probability of a certain state R, which is going to be P of the energy and the number of particles, and that is equal to E to the minus beta E minus mu n all over the grand partition function. And we have our entropy. S is equal to minus K sum over Pi ln Pi. And substituting in our probabilities, we have minus K outside of E to the minus beta E minus mu n all over our grand partition function times by, let me just skip down a line, times by the log of our probability distribution. Let's just put that there. And then I'm going to go minus ln z. So I've just split that up using the log laws. And now we can simplify this, where we end up with minus K sum over our probabilities and then you've got a log of an exponential, and so that gives us minus beta E minus mu n minus ln of z. We've got heaps of minuses here, so we can just get rid of them, make them all plus. And then we notice that we have our probability here and then variables here. And so when we sum over the probability times a variable, we end up with the average of that variable. And so what we have is K outside of beta times the average of E minus mu times the average of n plus, and because this isn't a variable, this is just a constant for the system, we're just going to sum over, we take that out the front of the sum, and because we're summing over the probabilities, we just end up with 1, so that's log of z. And so now that we have that, we realize that we can rearrange this to be minus kt log z is equal to e to the minus ts minus mu n. And so that's just me rearranging all these terms. I've dropped the averages because in the limit of very large, let's go, E is very large and N is very large, the fluctuations go to 0. And so I can drop the average and just take it as just the value itself. Now, this thing here is the grand potential. And if we just substitute in E, which is going to be Ts minus PV minus mu n, we end up with this is equal to PV. And so that is what we wanted to derive. So that should be minus PV. Sorry. And we just take the negative from both sides. Is there any questions about the answer to that exercise? I'll start the next exercise, which is 11.3, while questions come in, if they do, just so we don't have to worry about the lag. 11.3 is basically show that we can derive S, P, and N from partial derivatives of the grand potential. Now, I just got a question that was, where do the averages come from in that derivation? So let me just quickly do a little aside here. So we had, let's say for example, so we had this like e to the minus beta mu n, oh sorry, that should be e minus mu n all over z, and we had, and this was times by beta e minus mu n. We're summing over e and n essentially. We're summing over e and n. Actually, let me just make a new page because I've got 3 questions. All right, so in that derivation, we had this expression. So we had S is equal to K outside of summing over our e and n, e to the minus beta, e minus mu n over z outside of beta, e to the minus mu n minus log z. Now let me just split this up and we're just going to focus on this bit here. So we have this bit is En. We've got a beta out the front, e to the minus beta, e minus mu n, all over z, and then we also have minus mu outside of en, e to the minus beta, e minus mu n, all over z, and there's an n there. This is the probability of e and n. So is this. And a term that is essentially e to the n, e p e to the n is just equal to the average. So that's where the averages came from. So that should answer your question. Same thing as well for n. Now the next question was, could you go over the last step again? Why does the gram potential go to PV? Alright, so let's do that. It is just classical thermodynamics, nothing to do with statistical mechanics. So we just have E minus Ts minus mu n, and that's defined as, not a great omega. It's defined as omega g. And we know that E is equal to Ts minus PV plus mu n. So if we just substitute everything in, then what we get is Ts minus Ts minus PV plus mu n minus mu n equal to the gram potential, which is just equal to minus PV. So that's where that just comes from. Just classical thermodynamics, nothing more. And what version of the textbook is this was another question. I'm not sure what version it is because I have a pre-print copy. So yeah, I think it should be in every version. Whatever the current version is probably what Tim's got them from. So yeah, so this is the Hoch Statistical and Thermal Physics, an introduction. That's what the textbook is. And the next question was, I have a few questions about the content. Why are the canonical and grand canonical ensemble equivalent in the thermodynamic limit? Why do small energy fluctuations mean they are equivalent? It's not because of the small energy fluctuations, it's because of small particle number fluctuations. So the grand canonical ensemble, so you've got your grand canonical ensemble, will go to the canonical when n goes to infinity, let's say, like n large, because the fluctuations in the number of particles go to zero, and so what you've effectively done is it means that the particle number is fixed. So your n, there will not be any fluctuations. So there's no real flux of particles. So it's essentially going to be the canonical ensemble because there's no fluctuations in number of particles. Does that make any sense about that? Cool. All right, so let's now move on to 11.3, which is show that you can derive S, P, and N from the partials of omega g. And so this is essentially just classical statistical mechanics. So we just have this term here is going to be equal to, actually let me just write, the gram potential is equal to E minus Ts minus mu n. And so the derivative will be dE minus T ds minus S dt minus n d mu minus mu dn. And so we know that this term here is just T ds minus PdV plus mu dn. And so if we then substitute this in and subtract off all the terms that cancel, what we end up with is minus PdV minus SDT minus n d mu. And so we know, because of the first order homogeneous nature of the system, that d omega g is going to be equal to d omega g dv plus d omega g dt plus d omega g d mu. And so if we just equate the terms in this in these two equations, we see that the pressure is equal to minus partial omega g partial v at constant mu and t. The entropy is going to be equal to minus partial omega g partial t at constant v and mu, and the number of particles is going to be equal to minus partial omega g partial mu at constant v and t. All right. Any questions about this question? And after this as well, which problem would you like me to go through first? Or if you have any other questions as well about course content that I can answer. Alright, so our questions come in the derivation of the mean energy of a Fermi gas. Why do we need to include the spin degeneracy factor? Isn't it handled in the density of states factor? I also don't understand why mean occupancy times density of states is equal to the probability of being in a particular energy. I don't really understand how the mean energy has been derived. Okay, so let's go through the derivation of the mean energy of a Fermi gas. So let me just refer to Tim's notes. So you include the spin degeneracy factor into the density of states, but because you are trying to find the mean energy as well, you have to include spin degeneracy when it's necessary for the calculation of the energy, if that makes sense. If energy itself is a function of the spin degeneracy, that's when you should calculate, when you should include it. Don't understand why mean occupancy times density of states equals probability of being a particular energy. So mean occupancy of, like, let's say state R times the degeneracy of, let's say, state R, which is a particular energy. Actually, let me get rid of that and just say N of E, G of E, and you're saying why is this so? The degeneracy here basically tells you how many levels there are possibly to fill at a particular energy. And so this the mean number of particles is just the mean number of particles if the degeneracy wasn't present, if that makes sense. And so the degeneracy gives you the how many more states you can possibly have at that energy, and so that's why timesing these two together, you end up with the total number of possible occupancies of that level at energy E. Does that make sense? So you need to add extra multiplicities for specific levels, which is not included in this mean number of states. I'll have to probably get back to you on the why you need to include a spin degeneracy factor in both. It could also be that in the notes, the spin degeneracy factor is not included in the density of states explicitly, and when you're calculating the energy, you add it in there just in post. I think that's probably why, that it's not actually included in the density of states, and that's why it's there. But you'd have to probably ask Tim about that as well, because I'd have to read through his notes a bit more carefully and listen to his lectures. I've read all his notes, but I can't seem to see where that comes about. But yeah, yeah. So in part of his notes, it says we've rolled in the factor of 2 for the spin degeneracy and the definition of GE, and I'm not sure if that actually follows through every piece of the derivation as well. Yeah. Yeah. Okay. Isn't the probability? Yes, the probability is the amount of accessible states over the total states. That's true. But that's what this would be. This whole thing. Not just these ends as well, because you need to include these degeneracies, I think. Yeah. This tells you about how many particles could be in an energy state, and this tells you about the ways you could divide them up in that energy state. I think I'm probably not answering your question very well. Anyway, let's move on then to go through question 1, which was classical paramagnetism. We can come back to the probabilities for accessible states and the degeneracy a bit later as well if you want. Alright, so question 1 from the tutorial is, so we have a bunch of dipoles that and they're all localized, so there's no momentum element to it, and they're all non-interacting, and the energy is given by minus mu b sum over ni1 cos theta. And so the first part of this question is find an expression for the canonical partition function of the system in terms of a single dipole partition function. Well, this is easy. So we've got our total partition function, and because they're non-interacting, you've got the partition function for a single dipole, just raised to the power of n, because they're not talking to each other, so the number of states is going to multiply essentially as you add extra dipoles. So the second part of the problem is find an integral expression for the single dipole partition function of the system, and for this you'll need to include all possible orientations of the classical dipole. So what we've got is we've got Z1 is equal to 0 to 2 pi, 0 to pi, our solid angle, so let's call it d omega just for now, times e to the minus beta e, which is going to be a function of phi and theta, and this is equal to 0 to 2 pi, 0 to pi, sine theta d theta d phi, e to the minus beta plus mu b cos theta. So we have that. There are no other terms with phi in them, so we can just bring 2 pi out the front, and we have 0 pi sine theta d theta e to the beta mu b cos theta. Now, what we can do is we can do a change of variables here, where we've got x is equal to beta mu b cos theta, and we get dx is equal to beta mu b minus there sine theta d theta, and if we put this into our partition function, we end up with 2 pi, 0 pi, we bring a minus out the front, and we have dx on beta mu b, e beta mu b, oh damn it, that's just e to the x. Also these limits, sorry I've done them incorrectly. So the lower limit is just going to be beta mu b, and the upper limit is going to be minus beta mu b by just substituting in 0 and pi into x. And integrating this expression, what we end up with is, so we've got 2 pi on beta mu b outside of e to the x beta mu b minus there, and then beta mu b is b minus there, and what we then get is we have z1 is equal to 2 pi on beta mu b. Let's bring another 2 out the front. We've got e beta mu b minus e to the minus beta mu b all over 2, which is equal to 4 pi beta mu b sine of beta mu b. And so that's that. The next part of this problem is find an expression for the mean magnetic moment of the system in terms of a partial derivative of a single dipole partition function. So we've got the mean magnetic moment is equal to n mu average of cos theta, and that is equal to n mu, and I'm going to write this out fully. So we have 0 to 2 pi 0 to pi of cos theta outside of e to the beta mu b cos theta all over z. Oh, that's wrong z. Sine theta d theta d phi. Now, in terms of a derivative, we notice here that if we take d of d beta mu b of the z1, we end up with 2 pi 0 to pi cos theta e to the beta mu b cos theta sine theta d theta. And so that looks remarkably similar to this expression up here. And so what we can do is we can write mz is equal to n mu, and we then take, we've got 1 over beta mu, because let's just take the derivative in terms of capital B instead of the whole lot. So we've got beta mu d db of z1, and this was all over z, so let's bring z out the front. And so what we end up with after cancelling it is n1 beta 1 on z1 sorry to b, which is equal to n on b log z1 on b. So that's our final result, written very poorly in the corner. The next part of the question is then actually going ahead and calculating this. So we have our result from before, which is that the mean magnetic moment in the z direction is equal to, hold on. For a single dipole, so let's get rid of the n, we have 1 on beta dB, and let's write out our partition function for a single particle, the log of that, sorry, which is 4 pi sine of beta mu b all over beta mu b. And we see that some terms are going to contribute to this derivative and some aren't after we expand this log. And so I'm just going to put the things that are actually going to contribute here. So we've got log of sine beta mu b minus log b. And so doing this derivative, we end up with 1 on beta. We've got cosh beta mu b on sine beta mu b, and then we've got a mu b there, and then minus 1 on b. So this is going to be equal to, that's not right, it should be a mu and then a beta. So let's take this mu out the front and turn this into a coth. And then we get 1 minus 1 on b mu beta. This function here has another name. It's called the Langevin function. Sorry, that should be eta, where eta is equal to beta mu b. All right. And so I've just plotted this function here. So you can see in Mathematica. And so this function has, as a function of eta, has a steep slope up and then goes to 1 as eta increases. So that's as either b gets large or kt gets small. I've also plotted this function as a function of kt with increasing mu b as well. And so you can see those features there. We'll return to this page in a sec. So the last part of the question, or the second last part, sorry, is finding the mean magnetic moment per unit volume. And so what we have is m z naught is equal to n0 mu times the Langevin function of eta. And so we want to find this high temperature limit of this. And so if you Taylor expand this here, we can end up with 1/3 times eta, where that is just your mu b kt. And so just give me 1 sec, sorry. You can show this yourself as well, doing this Taylor expansion. You can also just plug it into Mathematica and it'll spit it out for you. But if we put this now all together, we end up with n0 mu squared b on kt. And then if we want this in terms of the magnetic field H, then we've got n0 mu squared mu naught H all over 3 kt. And so in the limit for finding the susceptibility chi, we just take this derivative of m naught with respect to that, and we find the limit as h goes to 0, and so this is just equal to n0 mu squared mu naught over 3 kt. And so that's our result there. The very last part of this problem is finding the heat capacity per dipole. So that's basically a specific heat capacity. So let's write little c, part 6, little c, and we know that's equal to the derivative of the mean energy dt, and we want it in units of kt. I mean k on 2. So the mean energy. So let's go back to our definition of the energy of the system, which is equal to minus mu b. Let's do it for a single particle, so let's not worry about that. Cos theta. And so the mean energy, which is just U1, is going to be equal to B mu minus then a cos theta. And this, as we've already found out, is going to be B mu. Does that have the right? I think I'm messing up. So it's minus B mu cos of mu B on KT minus KT on mu B. So this is our Langevin function from before. And then just finding the heat capacity, CH, is just finding this derivative with respect to T. And that is going to be equal to minus K UB cos. Did I miss something? No, it's fine. K outside of mu B KT squared cosec squared mu B on KT minus 1. So we have this here. That's just equal to shine squared to the minus 1 of that as well. And I've also plotted this. So if we go have a look at this Mathematica document that I had before, we have plotted the classical result. So this is in blue. So this is just going to be I haven't actually done it in units of KB on 2. I've accidentally done it on just KB. But our classical result, we end up with this blue line here as a function of KT on mu B. And so I just wanted to compare this to our quantum result, which was this orange line. And there's something interesting to notice. In the classical result, the heat capacity doesn't actually go to 0. And we know from the third law that the heat capacity should go to 0 as temperature goes to 0. And so that's a little bit of a failing as well of this model compared to the quantum result. So are there any questions about that question I just did? If there's no other questions as well, we can move on to a different question for question 3. Oh, here we go. Alright, so for anyone who doesn't know what the question is from, wait, hold on, okay, hold on. How do you know how to start off? Okay, so question 3 of question 1, find an expression for the mean magnetic moment of the system. The magnetic moment, mu, is just given by mu, this is, hold on. It's mu in the Z direction. And then this mu here is like a size cos theta. So you kind of just get it from the definition of the energy. That's how, really. Because we saw from the energy that mu I, which is a vector, is equal to mu cos theta. And that's going to be in the z direction because we know that the magnetic field is in the z direction. Actually, hold on. Let's just do it like this. Because it's timesing by the magnetic field in the z direction. That's how you know where to get the formula for the magnetic moment. So if we're finding the we know, sorry, let me redo a little bit. We've got our magnetization in the z direction, which is what we're looking for. The reason why we picked the z direction is because the magnetic field is pointing in the z direction. So we have this. The whole magnetization of the system is going to, so it's going to be times by a factor of n. And the magnetic moment of the system, let's just say average mu z, just to start off with. And this will just come from its orientation to the magnetic field, which is given by cos theta. That's the only way that you figure out how to get that. Does that make sense? So it's sort of like how to break it up into specific parts. And also just because, you know that you've got your coordinate system and the orientation off the z axis, is going to be given by a theta. And so that's kind of how you get it in terms of the in terms of that, mu is always going to be fixed for each dipole, so it's going to be like a fixed number. So that can always come out the front, and then your cos theta is just going to be an orientation term. Because if you project this onto this axis, to the z axis, then you'll end up with a cos theta. Cool. I hope that helped. All right, going back then to the question about in the derivation of the mean energy of a Fermi gas, why do we include a spin degeneracy factor? Could you tell me which lecture that's from, and I can specifically have a look at it? Because there's two different lectures that do energy of a Fermi gas. Are you thinking of lecture 9? Maybe we won't cover that then, if because they could have logged off the live stream. Is there any other questions then before we just wrap up? We just got a few more minutes left, and I can just maybe cover something before we go. It's in lecture 26. What do you mean by lecture 26? Because I know in Tim's lectures they're labelled from 1. Yeah, sorry. Tim's lecture 7. Okay, let's... Eight. Okay, let's have a look. Can you tell me a specific like page, or is it not that? Because I know on page 3, the degeneracy is added just directly to it. But then in other parts, it's actually not added directly to it, so I'm not sure. To me, it almost seems like an abuse of notation in that G is being used for 2 different things. So I'm not quite sure. So, here we go. Alright. So I think one thing to be careful of is that GE is not G. This refers to spin degeneracy, and this refers to just the degeneracy of the level. Sometimes you'll see this written as like a GS, which helps a lot. Let me keep looking. All right. So if you have a look at where it derives the energy, the GE doesn't contain this little g, and that's why it's out the front. That's from what I can tell. Because if you compare the form on page 11 to the form on page 18, GE is different in both cases, from what I can see. Because yeah, one has the 2 and one doesn't. Does that help? Yeah, so on page 13 is accounted for, on page 18 it's not. So, yeah. I have no idea. I think it's following the textbook as well. If you want to shoot him an email and say, ask him, then by all means go for it. So yeah. Cool. Is there any other questions? Oh, and did I get your question about the mean occupancy times density of states is the probability? Um, did I cover that well enough, or would you like me to go over it again? Okay, I'll just do a quick explanation of that. So, do you have a particular page where you've seen this, and then I can refer to it a bit better? Yeah, because that could help. Maybe maybe we can think about it this way as well. If we're trying to calculate an average of something, and that's going to be average n of okay. Let me just go back a little bit. These average n's are a function of energy, but energy is not actually the variable that's really changing. In a sense, it's E is a function of K. And so if you really think about it, N is a function of K. And so if we were to do everything properly, well, properly is not probably not probably the right word, but everything should be integrated over dk of whatever x is of k and k. And so what the degeneracy is basically saying is, let's rescale everything so that we can write things in terms of energy instead of writing them in terms of k. So this is basically giving you a rescaling of that, so everything makes sense. It's because that this k doesn't scale linearly with energy, and so you don't get that, because it's the energy is the surface of the sphere and k is the radius of the sphere. If I refer to the notes, 1819. Yeah. So maybe don't think about it as a probability per se. That maybe don't think about GE and E as a probability. Don't think about it like that. Think about it as something similar to it, sure. But the thing is that this is just allowing you to change your think about it as a change in variables for your probability. So if you have a probability that's like P of K, and you want to go to a probability that's P of E, then you need to do the trick where you have P of E is going to be equal to P of K of E dE dk, which is what was done in, I think, lecture 1 and stuff. And so this is sort of giving you this GE. It's rescaling your coordinates so you can change change your variables. Does that make sense? Maybe I should get rid of that. Well, if there's no other questions and comments about that, I think I'll leave it here. We've just run out of time anyway. This will be uploaded to YouTube, so just go to my channel. There's a link in the Tutes part. And I will also post the solutions to the problems we didn't get to. And so, yeah, I think we'll leave it there. If you have any other questions as well, feel free to email me and I'll try and get to you. Cool. Oh wait, hold on. We just got a comment. So NK, should NK be PK in the expression above? Sorry. So NK is related to PK. And so with the whole idea about mean occupation number is that if the mean occupation number of a particular level over R is equal to the probability of that level. Does that make sense? Because it's like it's frequentist, as in like how often will you see a particular occurrence, and then times it by how many occurrences you see, that gives you the probability. So if you, I guess that's probably the best way to say it. Let's imagine actually. Let's say you had n dice, you rolled them all, and then you wanted to look at the occurrence of a 1, 2, 3, 4, 5, and 6. You would get how many occurrences you got of each of those things, and then so the occurrences divided by the total number of dice would equal your P of R. Does that make sense? And so that's how those two are related. And I believe actually as well that because it's a little r, it's just it is P of R, because I think it is scaled by the capital N, although I'm not too sure. So yeah. All right. So I'll just leave it there now. Thanks guys. I will see you all next week.